Hello everyone, and welcome to the Introduction to Tree Methods lecture. In this lecture, we'll discuss decision trees and random forests as machine learning models. If you want the mathematics behind these topics, go ahead and read Chapter 8 of an Introduction to Statistical Learning. Let's start off with a thought experiment to give a little bit of motivation behind why we would use a decision tree method. Imagine that I play tennis every Saturday and I always invite a friend to come play with me. Sometimes my friend shows up, sometimes not. For him, it depends on a variety of factors, such as weather, temperature, humidity, wind, etc. I start keeping track of these features and whether or not he showed up to play with me. And my data looks something like this. Each of these columns represents a feature and each of the rows represents a certain day. I go ahead and for each row or day, take note of the features, and finally, at the final column, I have a label whether or not my friend came to play with me. So you can see on the first day, I have temperature mild, a sunny outlook, humidity of 80, windy, it was not, and my friend came out to play. However, in day 2, it was a hot temperature, sunny outlook, 75 humidity, it was windy, and my friend did not come play with me. I can build a decision tree off of this process. I want to use this data to predict whether or not my friend is going to show up to play. And an intuitive way to do this is through a decision tree. And this is what a decision tree may look like for the data I just showed. In this tree, we have nodes, and nodes split for the value of a certain attribute. We can see here we have outlook nodes, humidity nodes, and windy nodes. So each of these attributes are nodes. And then we have edges. Edges are the outcome of a split to the next node. In this tree, we also have a root node. That's the node that performs the first split. So in this particular example, the root node is the outlook feature, where I perform the first split and I split into the possible categories of sunny, overcast, and rain. And then those will lead to other nodes, such as humidity and windy. The colored nodes, which are yeses and nos, are leaves, and those are the terminal nodes that predict the outcome. Let's go ahead and discuss an intuition behind splitting on these nodes. Imagine now that I have this data with 3 features, X, Y, and Z, and I'm trying to predict 2 possible classes, Class A or Class B. Splitting on Y gives us a clear separation between classes. If I ask, does Y equal 1? I get perfect separation of the 2 class instances of Class A and the 2 instances of Class B. Again, if I go back and check out this imaginary data, note how the Y feature split the classes perfectly. And also note how the X and Z features don't split the classes perfectly. Meaning, I could have also tried splitting on other features first. If I split on X first or Z first, I don't get proper separation of those classes. Entropy and information gain are the mathematical methods of choosing the best split. Go ahead and refer to the reading assignment if you're interested in the mathematics behind this intuition. But the actual intuition is just trying to choose the features that best split your data. This is called trying to maximize your information gain off of this split. Again, refer to Chapter 8 if you want more information on the mathematics behind these topics of entropy and information gain. Now let's talk about random forests as a way to improve performance off single decision trees. The primary weakness of decision trees is that they don't tend to have the best predictive accuracy. This is partially due to the high variance, meaning that different splits in the training data can lead to very different trees. Bagging is a general purpose procedure for reducing the variance of a machine learning method that's discussed in Chapter 8 of the reading assignment. We can build off the idea of bagging by utilizing random forests. Random forest is just a slight variation of these bagged trees that has even better performance, which is what we're going to be discussing and coding out in R. What we do with a random forest is we create an ensemble of decision trees using bootstrapped samples of the training set. Bootstrapped samples of the training set just means sampling from the training set with replacement. However, when we're building each tree, each time a split is considered, a random sample of M features is chosen as a split candidate from the full set of P features. the split is only allowed to use one of those M features. A new random sample of features is chosen for every single tree at every single split. For classification, this M, random sample of M features, is typically chosen to be the square root of P, where P was the full set of features. You may be wondering, what's the point of using random forests? Well, suppose there's one very strong feature in the dataset, a feature that's really strong at predicting a certain class. When using bagged trees, that's that bootstrap sampling, most of the trees will use that feature as the top split. That's going to result in an ensemble of really similar trees that are highly correlated, which is something we want to avoid. Averaging highly correlated quantities does not significantly reduce variance. By randomly leaving out candidate features from each split, random forests are going to decorrelate the trees, meaning making the trees independent of each other, such that the averaging process can reduce the variance of the resulting model. So we won't be affected by features that really strongly predict the class data. Now that we've taken a look at the theoretical background behind decision trees and random forests, let's go ahead and move on to seeing some examples with Python. We'll start off by taking a look at a small example dataset of kyphosis, which is a medical spine condition, and we'll look at patients and try to see or predict whether or not a corrective spine surgery was successful. Then, for your portfolio exercise project, we'll go ahead and use loan data from Lending Club to predict default rates on some real-world data. Thanks everyone, and I'll see you at the next lecture.